Hello everyone, my name is Zahra and my team and I will present to you this tutorial to explain the lattice Boltzmann method in the context of computational fluid dynamics. Here is the outline for the presentation. We'll start by giving you an overview of lattice Boltzmann method and its historical background before we dive into technical details of the governing equations. After that, we'll go through a hand calculation example using LBM and we'll follow with a code representation of the method. Finally, we'll wrap up with examples of LBM applications in different fields. I'll present to you the introduction, historical background, and general principles. Then Stephen will present the governing equations, hand calculation, and numerical example. And finally, Jushan and Fahad will wrap up with the applications. So to start off with, here is an overview of what LBM is. The Lattice-Boltzmann method is used in the field of computational fluid dynamics to simulate fluid flow. It is a finite difference method used for solving the Boltzmann transport equation, which bridges the gap between the microscale and macroscale. And we'll elaborate more on the difference between these different scales on the next slide, so hold on to that thought. LBM considers a collection of particles whose behavior is represented using distribution functions. And these particles move and interact on a lattice grid. They follow simplified kinetic equations known as the Lattice-Boltzmann equations, which describe their collision and propagation behaviors. Now, from a computational point of view, LBM is hyperbolic and it has high performance, so it can be efficiently solved explicitly and locally on parallel computers. Generally, LBM is used to model simulating complex fluid flow, such as turbulence and phase transition, because it captures more fluid behavior compared to CFD conventional methods. Now, to better understand the fact that LBM bridges the gap between microscale and macroscale, let's elaborate more on the difference between these scales. So, when we try to simulate fluids, we can observe them or represent them on different possible scales. One option is looking into the microscale, where a medium is assumed to be made of a huge number of very small individual particles, which offers an accurate, detailed representation of molecules and their interactions. However, the cons of this approach is that it is computationally intensive and it has limited spatial and temporal scales because we're trying to track a huge number of molecules. Also, because we're looking at chaotic individual molecules, there are no definitions of phenomenological properties, for example, viscosity, temperature, and pressure. Moreover, in many applications, such as flow in porous media, it's not usually useful to look at individual molecules' behavior, and we're more interested in bulk fluid behavior. On the other hand, the extreme opposite scale would be the macro scale, in which the domain is discretized into finite volumes, elements, or grids, depending on the method utilized, and each finite volume, element, or node is assigned a collection of particles. So, the pros of this scale is that it is more computationally efficient and more applicable to capture a system behavior on a broader level. However, one can argue that it lacks detailed information in some applications, and that it relies more on assumptions and simplifications. Now, a scale that would offer something in between, which could be useful to combining benefits of the other two scales, is the mesoscale. The mesoscale is what is used in the Lattice-Boltzmann method, in which collections of particles are represented by a distribution function. This offers an intermediate level of detail, and it reasonably captures mesoscopic phenomena. However, it is still somewhat complex and computationally expensive. Moving on, we're going to switch gears to present an overview of the methods used historically for modeling or simulating fluid behavior. So before the method of LBM was invented, there were many other similar methods or models that were mostly theoretical, but had similar math of and close connections to the Lattice-Boltzmann equation and lattice gas automata. An example are the discrete velocity models and the beam scheme. However, these methods were mostly used as theoretical models to study analytical properties of fluids, and they were not intended to be used as computational tools. Another example of these models is the HPP lattice gas automata. This was the first LGA to be introduced as a single-speed lattice gas automaton model on 2D square lattice space, and historically, this is where the LBM method has originated from. Later on, in 1986, the first 2D lattice gas automaton model was proposed specifically for the purpose of computational fluid dynamics. And then, a 3D lattice gas automaton model was introduced soon afterwards. So to elaborate more on lattice gas automata in general, for LGA, the word lattice suggests that the method works on a lattice that is usually regular. The word gas indicates that what's moving on this lattice is gas, and this gas is represented using Boolean particles, that is 0 or 1. And the word automata implies that this gas moves following certain rules. Moreover, in LGA, particles' velocity, time, and space are discrete, and one iteration involves a collision step and a propagation step. Also, like any other method, LGA has its disadvantages, such as intrinsic noise, large numerical viscosities, and unphysical velocity-dependent pressure. So, the history in the literature suggests that the subsequent contribution to the lattice gas automata and the Lattice-Boltzmann equation by Boltzmann, McNamara, and Zanetti, among others, eventually gave birth to what we call the Lattice-Boltzmann method. Hence, when we talk about the LBM methods in this presentation, we explain it mainly in terms of both the lattice gas automata and the Lattice-Boltzmann equation. That being said, LBM method offers the advantages of numerical stability in computational fluid dynamics, and also it's successful in simulations of fluid flow with complicated boundaries and or complex fluids such as turbulent flow over structures with complicated geometries. Also, multi-component and multi-phase flow in porous media. Nevertheless, LBM still has some limitations when it comes to turbulent flows at high Reynolds number, which is a potential area of improvement. With that in mind, now it is useful to try to tie the historical background with the general principles and knowledge of different scales that we have explained before, which will allow us to better understand the motive behind LBM method. So in the context of understanding fluid behavior, a fluid is considered a discrete system comprised of a large number of particles that can be described by different ways, as we've explained before. One way is to view the fluid as a continuum in the macro scale. And the most famous equation for this in fluid dynamics is the Navier-Stokes equation, which describes temporal and spatial density, momentum, and energy. So the challenge with solving Navier-Stokes partial differential equations analytically is that it has nonlinear terms. Therefore, with the advancement in computational power, the CFD methods resorted to solving Navier-Stokes numerically, where all particles are represented by a nodal value or averaged over a finite volume, or assumed to vary linearly or bilinearly from one node to another. Nevertheless, even numerically, solving Navier-Stokes equations is still complicated for many cases, such as multiphase or multi-component flow, as we need to know the equation of state, which is typically unknown at the interface. On the other hand, when viewing the fluid from molecular dynamics point of view, whose methods describe fluids on the microscale, you have molecules going in all directions and everything is very chaotic. So technically, there are no definitions of phenomenological properties such as viscosity, temperature, and pressure. In this case, because you're attempting to track the individual behavior of a huge number of molecules, this becomes exceptionally costly in computational power. Therefore, to establish something in between these two extreme representations and two extreme methods, Boltzmann was the first to establish the link between the macroscale and the microscale in attempt to establish a better understanding of fluid behavior. And this intermediate scale is called the mesoscale, as we alluded to before, where the relationship between temperature, velocity, and kinetic energy can be represented by a Maxwell equilibrium distribution for an ideal gas. In this case, pressure and velocity are calculated by evaluating hydrodynamic moments of the distribution function. However, the early forms of Lattice-Boltzmann equation accounted for only gas at rest, or equilibrium. Therefore, it was further developed to account for non-equilibrium conditions. And to accomplish this step, a concept called distribution of particles in phase space needed to be utilized, which in essence is the probability of a particle to be at a certain position and velocity at a certain time. So to summarize this, the Lattice-Boltzmann equation was developed for non-equilibrium conditions once the distribution in phase space was accounted for. And this was for particles in non-collision state. And then the equation underwent a complex derivation and a collision operator was introduced to account for collisions. And as we mentioned earlier, the subsequent contribution of Boltzmann, McNamara, and Zanetti, among others, along with the integration of lattice gas automata with Lattice-Boltzmann equation, resulted in what we call the Lattice-Boltzmann method. We will dive more into details about the governing equations of the Lattice-Boltzmann method in the next part of this presentation.
We are going to present the governing equations of the Lattice-Boltzmann method. The Lattice-Boltzmann method is built on top of what is called a distribution function. A distribution function is a function defined in the hyperspace of macroscopic velocities and positions, and it describes how a cloud of molecules is moving in a given direction. Each molecule has its own velocity and its own position, but we only care about the behavior of the group. So as we see in the image, that we have a lattice, and we are going to develop this more in next slides, but each node represents cloud of particles. And this is one fundamental difference from molecular dynamics. This distribution function, which is given in each node of the Lattice-Boltzmann method, gives the probability of finding one particle not in a specific velocity, but a range of velocities. This means that the probability of finding a particle in one velocity is 0. Now, The Boltzmann transported equation is a statistical description of a system, which is a cloud of molecules or particles, which is given a direction and which is moving in a specific direction, sorry, and they can be applied an external force. So this equation describes how the distribution function evolves in time and space, and also includes the total change given by the process of the molecules colliding against each other. And this is given by the collision operator, which is the rate in which the system particles approach equilibrium. So the process of collision between molecules, it's a process of exchanging of energy, and it's the way in which this system is going to approach equilibrium by transferring energy to other molecules. This operator is difficult to describe, but there are two approximations for it. One of it is the BJK approximation, which uses one parameter called the collision frequency, or it is also called the inverse, the relaxation time. And there is another approximation that it's called multi-relaxation time. And the difference is that if we have multiple distributions or multiple ways of describing the system, we can have one relaxation time per description of the system. These approximations are built on top of what is called an equilibrium distribution. This means how the system would behave if it were a equilibrium. This equilibrium distribution is given by the Maxwell-Boltzmann distribution function, which is defined in the velocity space, and it describes the probability of finding a particle in an interval of velocities. Also, it takes into account that the whole cloud of molecules could be moving at a macroscopic velocity u. So, this is the basis of the method, and the way of relating this distribution function with the macroscopic properties of the system is by averaging, by using the distribution function. So it's just integral multiplied by the molecular weight, and you can find the density. And once you find the density, you can find other properties just like the macroscopic velocity and the kinetic energy of the defined mathematical foundations behind the Lattice-Boltzmann method. As the Lattice-Boltzmann method is not an analytical solution to the Boltzmann transport equation, but a numerical solution, we want to discretize this equation, and the way of doing so is by stating that each of the lattice or in the mesh is going to have its own distribution function, and the Boltzmann transport equation is going to be solved for that specific node. So we define that every node in the lattice or every linkage in the lattice has its own distribution function and equilibrium distribution function. We want to discretize the derivatives in time and space. By doing this, we obtain the two main steps of the Lattice-Boltzmann method, which are the collision and the streaming. Moreover, we are not going to use the exponential description of the Maxwell-Boltzmann equilibrium distribution, but we are going to truncate it to the second order of the Taylor series expansion, which is the one that you see there. Now that we have discretized the Boltzmann transfer equation, the next step is to select the lattice arrangements. So a lattice is defined by its dimension and the quantity of nodes inside the lattice. So these are the nodes or linkages that we mentioned, and each node has its own distribution function. It is important to select the right lattice arrangement because each lattice has its own weighting factors. This means that If you select D1Q, Q2 for example, it's going to have different weighting factors than selecting D1, Q3. Also, there is a speed of some parameter that is dependent of the lattice arrangement. Expanding to the streaming and collision process of the lattice Boltzmann method. As I told you before, the collision process is the calculation of how the distributions are affected by the internal behavior of the cloud of molecules and by the way the molecules inside the cloud collide against each other. So this step is okay, how are the molecules approaching equilibrium or how's the system approaching equilibrium? And the next step which is the streaming, it's okay, now that we updated the distributions, how this information propagates in the system. Lattice-Boltzmann method must account for the system interaction with the surroundings, and this is done by the boundary conditions. The system is at equilibrium at the boundary, therefore, the non-distribution equilibriums at the distribution at the boundary must be zero. What this means is that if we have the the value of the property we are trying to find with the Lattice-Boltzmann method, the restriction is the sum of the non-equilibrium part with the equilibrium part of the system at the boundary, which has this value included, must be zero. This is the way of expressing the boundary conditions. Also, the non-slip conditions can be implemented this way, and the name of this is the bounce back boundary condition. Important step for using the Lattice-Boltzmann method is to non-dimensionalize and scale the PDE that describes the behavior of your macroscopic system. This is because we need to establish an equivalence between the macroscopic mm, behavior, which is described by the PDE, and the mesoscopic behavior, which is described by Lattice-Boltzmann. And this is done via non-dimensional parameters. So these non-dimensional parameters, which may take care of the scale, should be equal for both methods. Since these non-dimensional parameters should be equal, in the case, for example, of the one-dimensional diffusion equation, this is the equivalence that must be stated. And the parameter alpha should be selected such that the number of lattices and time steps respect the equivalence between the scales. We presented the main ideas behind the Lattice-Boltzmann method. Now we're going to show how this is used in practice. So, for example, if we have an aluminum rod of 4 centimeters with a constant thermal diffusivity, this means this could be described by the one-dimensional diffusion equation, in which on one side it has a constant temperature boundary at 373 Kelvin, and the whole aluminum rod it's T low, which is almost 300 Kelvin, and we want to know the distribution of the temperature after 4 seconds. So what are we going to do is we're going to apply the Lattice-Boltzmann method to solve this problem. Then we need to select is the type of lattice we want to use to solve the problem. For this problem, we are going to use 4 D1Q3 lattices as it is shown in the image. The second step is establish the scale and the equivalence between the scales. And for this, we can select the value of alpha or the amount of time steps. In this case, we are selecting the amount of side steps and we are saying, okay, the amount of time steps is 4. Now with the thermal diffusivity, we calculate the relaxation time omega, and we have our equations for the diffusion processes, which are the one for collision and the one for streaming. However, since the temperature is scaled, this means that the theta, which is the normalized temperature, is equal to 0. This means the whole rod is at the lowest temperature, and as the macroscopic medium is static, this means it is not moving, it has no macroscopic velocity, the equilibrium distribution is just the weighting factor for the lattice we selected, which in this case is for the node 0, 4 over 6, and for the 1 and 2, 1 over 6. And the initial conditions is that every distribution is at the lowest temperature. Since every distribution is at the lowest temperature, this means that the value of the distribution is 0 for every lattice. The first iteration, the collision and the streaming, it's going to remain equal. The only thing that it's going to change is the boundary condition, which is applied at the first lattice, and specifically at the node number 1. Iteration, now we have a value for F1, and this means we can update the rest of the distribution functions for the lattice 1, and we can stream this information to the second lattice because we already have a change in temperature in the road for the first lattice. In the next iterations, we follow the same procedure of calculating the collision step and then spreading the information to the other lattices. And at the end of the fourth iteration, we see that the lattice 4 has experienced an increase in temperature as well. Now we are going to look at a similar example, but this time we are going to implement the Lattice Boltzmann in code, and we are going to explain how each part of the process is done via coding. For this example, we are going to calculate the temperature distribution for a slab which is at already normalized and it has the temperature at its lowest and it has a high temperature equal to 1. It has 10 units of length and we want to find the temperature distribution at the time step 200. So for this specific case, we are going to have a heat diffusivity of 0.25 and we're going to use 101 D1Q3 lattices to solve the problem. The first step is to initialize the values and the distributions we are going to use for the mesh that we have, that is a mesh of 101 lattices of the type D1Q3. Moreover, we know that the weighting factors for this specific type of lattice is 4 over 6 for the node that is static and 1 over 6 for the nodes that are spreading, that are going to be streamed. Moreover, we want to calculate our property, which we are going to call rho, but it could be theta. It's just the result of averaging the distribution function as we are actually solving the diffusion equation for heat. So this means we are going to find the normalized temperature. Initializing the properties, the weighting factors, and to establish the value of the distribution functions at zero. We follow the steps of collision, which is called, as we saw in the formula, 1 minus omega multiplied by the value of the node, so omega multiplied by the value of the equilibrium distribution function. The streaming of the information, which is just spreading to the other F1 nodes and the other F2 nodes in the other lattices, and applying the boundary conditions. In this case, we only have boundary condition to one side of, of the 1D slab. We are applying via the T-wall value, and after this process, we are calculating the, the sum of the distribution functions for each lattice, and we obtain the macroscopic property at that lattice. After applying this process for multiple time steps, we see how the temperature is changing in the x direction, which is expected, and we have a higher temperature in the nodes that are nearest to the boundary, which is also expected, and lower temperatures to the nodes that are further away.
Hi, I'm Joe Chen. I'm going to give you some examples like the LBM can be used for applications in those numerous fields. So LBM can have those like applications around those industries and scientific fields. Here I will give you like 9 examples in different fields. So the first one is in the oil and gas exploration field. LBM can be employed to simulate fluid flow in porous rock formations to optimize oil and gas extraction process. And by understanding how fluids move through the subsurface reservoirs, those energy complaints can improve drilling techniques, enhance production rates, and maximum resources recovery as well. So also in the material science and the nanotechnology field, LBM are applied to simulate fluid flow and particle interactions at nanoscale for those material science and nanotechnology. These simulations can help those researchers in the similar field in designing novel materials, studying surface phenomenon, and developing advanced nanoscale devices. And in the automotive industry, LBM can be used to simulate those airflow around the vehicles to optimize aerodynamics designs, just like those hypercars. And also it can reduce drag and improve fuel efficiency by accurately predicting airflow patterns. Those car manufacturers can design vehicles that are more fuel efficient and have lower emissions. Um, in the biomedical engineering field, LBM can be used to simulate the blood flow in arteries and veins to study hemodynamics and investigate cardiovascular diseases. These simulations help researchers and those doctors to understand blood flow dynamics, assess the risk of arterial diseases, and design better medical devices such as the stents and artificial heart valves. And in the environmental engineering field, LBM are utilized to model pollutant dispersion in the atmosphere and water bodies, helping in environmental impact assessment and the design of pollution control measures. So by simulating the movement of pollutants, environmental engineers can evaluate the effectiveness of mitigation strategies and also safeguard public health and ecosystems. Next, in the macrofluids and lab-on-chip devices, LBM can be applied to simulate fluid behavior in macroscale channels and chambers in the macrofluidic devices. These simulations help those researchers in this area to design and optimize macrofluidic systems, just for example, such as medical diagnostics, drug delivery, and chemical analysis. And in the renewable energy, LBM are used to model fluid flow in wind farms to optimize the placement and the design of the wind turbines for maximum energy capture by simulating wind patterns and turbine interactions. Those renewable energy companies they can improve the efficiency and profit of the wind power generation. In the climate modeling, LBM are used to model the atmospheric and oceanic circulation patterns and study the impact of climate change. These simulations help scientists understand climate dynamics, predict future climate scenarios, and formulate policy for climate adaptations and mitigations. So the last one in the aerospace engineering, LBM are used to simulate the fluid flow around the aircraft. I think it's the same of the airflow and the spacecraft to optimize vehicle performance, stability, and control. In that so, aerospace engineers can design safer and more efficient aircraft and the spacecraft by accurately predicting aerodynamic forces and moments. In the oil and gas field, these researchers they apply to macro structure images of these kind of sandstone, and they accurately replicate experimental setups, building close agreement in drainage capillary pressure curves and steady-state relative permeabilities. In the material science and the nanotechnology field, here is an example. Alexandra in 2023, their group used LBM solutions to characterize the liquid-solids interface by quantifying the total length of the triple line and the wetting area. So other than the normal wetting experiments, they can not only get the contact angle and the IFT, they can also to quantify the triple line and the wetting area. So they enable the characterization of impregation within textures for complex mixed regimes. So here is another example in the automotive industry. This guy, they use LBM solutions to investigate the aeroacoustic phenomena, particularly in low-speed fans and engine cooling modules, enabling direct noise prediction, source identification, and comparison with the experimental setup. Keep going. So in the medical engineering field, these researchers they simulate the transient blood flow in the biologically inspired geometries, addressing numerical challenges associated with non-Newton characteristics using Quantum law rheology model and demonstrating its accuracy through benchmarking against analytic solutions and applications to complex configurations such as carotid artery sections. In the environmental engineering, They use LBM to simulate the road transport pollutant dispersion and the urban macro scale, overcoming stability deficiencies for high Raynaud number flows, and successfully coupling with a macroscopic traffic model and emissions model to analyze transient flow features and concentration levels in complex urban
Moving
geometries.
on to the world of microfluids, the lattice Boltzmann methods offer exponential capabilities that are crucial for the development of lab-on-a-chip devices. These devices are integral in fields such as medical diagnostic and biomedical assays. One of the key challenges in microfluids is controlling fluid behaviors at the microscale, especially managing interfaces and capillary effects, which are common in such small environments. Here, LBM provides the precision needed for effective manipulation of these fluid properties. Recent advancements have integrated LBM with sensor technologies to create adaptive microfluid systems. The system can dynamically adjust fluid path and flow rates based on real-time data, enhancing their utility in applications like personalized medicine. In this slide, we can see that LBM is suitable for studying gases flows in MEMS due to its ability to handle different flow regimes, particularly when the quantum assumption fails due to the small scale of the system. Also, the Kinson number is crucial for determining the appropriate simulation approach. For Kinson number less than 0.01, the quantum assumption holds, but as Kinson number increase, non-quantum effects become significant. So, we can see in figure 1 that it provides a clear visual representation of how the Boltzmann method can be effectively applied in microfluids, especially for modeling gases flows in microchannels, which is particularly relevant in MEMS applications. Moving on to renewable energy applications. The lattice Boltzmann method not only enhances the design of wind turbines but also extends its utility to hydro and tidal energy systems. It's adept at simulating fluid structure interactions, a crucial factor in optimizing the durability and efficiency of turbines. LBM's capability to predict the environmental impact of renewable energy installation ensures that our energy solutions are not just effective but also harmonizes with the environment. This is key to sustainable development. Looking forward, LBM is set to revolutionize the design of bio-inspired energy systems and next-generation renewables. These systems aim to mimic natural processes, promising higher efficiency and reduced environmental footprint. In this slide, we can see that figure 1 illustrates the lateral and vertical meandering, providing a clear depiction of how wake behaviors vary in different simulations, which can effectively demonstrate the complex dynamic captured by Boltzmann method. Moving to the next figure, which is figure 2, the graph compares the accuracy and computational performance of various simulation models, and it highlighted the efficiency of lattice Boltzmann method in wind farm simulation, which shows how lattice Boltzmann method is good for predicting environmental scenarios. These figures provide compelling visual aid for illustrating the effectiveness and application of lattice Boltzmann method. Moving on to climate modeling, the lattice Boltzmann method significantly contributes to our understanding of complex weather patterns and ocean currents, thus enhancing the accuracy of climate models. This is crucial for predicting and preparing for extreme weather events. LBM is a cornerstone in several international cooperative efforts to improve global climate models. These enhanced models are not just academic exercise. They inform and influence global policy decisions, shaping our response to climate challenges. Improved model accuracy aids policymakers in crafting strategies that are both effective and informed, ensuring that our approach to climate challenges is proactive rather than reactive. In this slide, Figure 1 shows a sketch of the geometry for the wind-driven ocean, as you can see in 2D, which can help illustrate the setup of Lattice-Boltzmann method application. And as you can see in figure 2, it shows the visualization of streamlines after 15 weeks of integration for the barotropic model of wind-driven circulation with a realistic land mask. It also includes a cool bar indicating the velocity magnitude, which can effectively demonstrate the results and impact of applying the Lattice-Boltzmann method in wind farm simulation. Now moving on to the last application, aerospace engineering. In aerospace engineering, the Lattice-Boltzmann method extends beyond the traditional aerodynamics to simulate alternative fuel behaviors within aerospace engines. This research is crucial for designing engines that are not only more efficient but also environmental friendly. LBM also prepares us for the final frontier space. It stimulates environmental conditions that our spacecraft might encounter on other planets as essential aspects of designing vehicles for external exploration. Furthermore, educational programs in aerospace engineering increasingly utilize LBM, providing students with realistic simulations that prepare them for the complex challenges they will face in their careers. So, we know that LBM is important in aerospace engineering, and as you can see in figure 1, the graph displays the comparison between the results of a 3D LBM and Navier-Stokes simulation at specific conditions, highlighting the difference in drag and lift coefficient. This can effectively demonstrate the effectiveness and comparative analysis of the LBM in flapping wind aerodynamics. And moving on to figure 2, we can see that the figure provides contour plots of pressure and velocity at run number 100 using the 3D Lattice-Boltzmann flexible wing simulation. It shows detailed visualization of the flow dynamic around the wings, which is crucial for understanding the impact of LBM simulation on wing aerodynamics. At the end, these visuals provide and illustrate the complex fluid dynamics involved in LBM simulations for flapping wing aerodynamics and enhance the understanding of its applications and benefits. At the end, thank you for listening to our presentation. This is our reference page, and following the reference page is 10 multiple choice questions.